Hello everyone. I've made this recording to show you how we can use H++ in our course to compare the amino acid residues in terms of their protonation of side chains with your mutant proteins. So right now, as you can see on my screen, I'm on our Canvas page, and under the bioinformatics module, I have an H++ page. So H++ is a program that allows us to calculate the pK values of all the titratable groups in a protein. So this requires that we know our amino acid side chains very, very well. So you want to make sure that you brush up on those if you don't remember from last semester. So first I'm going to do is I'm going to go to the H++ website, and I'm going to hope that it remembers my login. This happened quite a lot. So we did this in class, and I have to continue to tell it that yes, I believe it, that it's a safe site. The other thing that happens with me, it tells me that my password's incorrect, but I in fact logged in. And the reason you want to create an account is because if I hit view submissions, you can see what I've tried to do. So I've done these recently. Dr. Bell gave a summer workshop in the summer of 2020. So that was when I was following along with the workshop. I have access to everything that I've done. Um, so I'm following a PowerPoint that Dr. Bell gave us, and it is posted on Canvas so that you can look at this. So what we want to do is we want to look at the effect that our mutations have on structure. There could be effects in the immediate vicinity in terms of a lot of you are mutating titratable residues to non-titratable residues and vice versa. So it can affect the protonation of side chains in the vicinity. But it could also be at some distance from the mutation too. So, all right. So I'm going through some of these slides. So again, the slides can tell you a lot more information about the program and how it works. So what I'd like to do, I guess, is just to run this, and then we can see what the data look like. So I'm going to go to process the structure, and then I'm going to choose file. So if I'm going to go to my G drive, because I had this in class. So I have my PDB files that I used for the wild type that I used with AlphaFold. So this right here, this is the our variant 3 of the cytosolic MDH1 using AlphaFold. So that's the one. That's the one that I want to use. So you'll be using your mutant protein that you folded using AlphaFold. So that's what I want to use. So I'm going to hit open, and then I'm going to hit process file. So it says that I was successful, and says it should take about 4 minutes. It might actually be faster than that. Okay, it says the number of titratable sites in this is pretty high. So I'm going to keep all of these at their defaults, but one of the things you can do is you can run virtual experiments where you change the dielectric or the salinity or the pH. The one thing that Dr. Bell says he does is he changes the solvent box to cubic. So I leave everything else the same, but I save that as cubic. And then I hit process. So, so I should get something that will tell me how long this will take. And usually I don't get a blank screen. I think what I'm going to do is I'm going to pause this and then just come back when I get my results. Okay, so I paused the recording and now I'm back. It didn't actually take that long, maybe just a few minutes. So when the structure has been processed, hit view results. So, so a fun thing that you can do is you can look at the titration curve. For example, if I did, so here it has the N terminal and then all the titratable residues and then the C terminal. Interesting thing about this is that the residues don't always have the same pKa values as they do in the free amino acid structure. Okay, here's his 205, for example, and that is one of our histidines in the active site. So a free histidine would be about 6, and this is about 7. So if you click on this, it actually will give you the titration curve. So the way that they do this is that this his 205 is at 7. So if you look at the halfway, so if I look halfway in between and drop a line down, I get 7. So this shows you the titration curve from which these values are derived. So anyway, so this is maybe kind of interesting to look at that. So the files that you want to look for are these two right here. So what's nice about the file is that they save it. So this actually tells you the salinity, the pH, and the dielectric constants. They're actually in the file name. So this lists all of the pKa's and their titration curves, and this lists the residues that contribute to each pK shift. And then this is a PDB file of the predicted protonation state. So, so these are really the only 3 files that you have to download. I'm not going to download them here because I already did not download some them, so I want to show you what I got. So, also the other thing to remember is that the file name is the same, so when you download it, you have to make sure you don't rewrite over the other one. So here's my first file right here. So it lists all the titratable residues and sort of like a first kind of calculation of the pK, but then this is from the titration curve. So they sort of run simulated titration curves on all the titratable residues. So this is the column that you want to pay attention to. H++ can calculate pK values between 0 and 12. So for example, if there's a pK that's greater than 12, it'll just say greater than 12. So anyway, so this will list all of the pK values of all of the titratable residues. I did not go on beyond the list of the titratable residues because the next thing that I was interested in is the contributions. So for example, so this up here shows what these values mean. Actually, to back up just a little bit, when you click these links to download them, you'll just get a table of numbers. So what you're going to want to do is you want to go to your browser and then print to a PDF. So that's how I got those PDF values, is I actually had to open it in my browser and then print to a PDF. All right, so let us go back here. So that was the PDF. The other thing that you can do is you can export to Excel, which we did do in class, but we found that actually we had some difficulty. I think you have to have a paid version of Adobe, which I didn't have in the classroom, because I had to log in, which I didn't do. So there's that, but we found that one of the files was actually a little bit difficult to read if we put it into Excel because the conversion wasn't smooth. Okay, so if I go to the second file, then this will tell me all of the sites, and then it will list all of the residues that contribute to that pK. So you can see that this is a 33-page file, so it's quite a long file. But you don't have to pay attention to everything. What you want to do is you're going to want to find your mutation. So for example, if I say I looked at this aspartate right here. So aspartate's normally negatively charged. So what this lists in this column, so the first site is the first number is the background contribution of non-titratable groups, and the last one is the interaction with the titratable groups. So so if I just sort of randomly pick, I think I was at, where was I? I don't remember. Okay, say I was at ASP18, for example. So what this does is this tells me ASP18, and everything listed below is going to tell me what contributes to that pK. So aspartate, so actually I'd have to go back here. If I go back here, aspartate 18, its pKa is 4.674. So if I look at the other residues that contribute to that, I can see that if I have an arginine, the arginine is going to influence that pK by making it lower. So that's what that negative charge means, because arginine is positive. So arginine is going to want the aspartate to be negative. So if the aspartate's negative, it's lost its proton and its pKa is lower. Phenylalanine is not titratable. So any place where you see a 0, there might be some kind of electronic effects or van der Waals forces or something like that that might influence the pK. But because it's not a titratable residue, the value here is 0. Another aspartate nearby is going to make the pKa of this thing go up, because otherwise you'd have 2 negative charges. So if you look at this, you can see any nearby positively charged amino acids like arginine and lysine, and here's another arginine that's nearby, another lysine, they would all want the pKr of the side chain of the asp18 to go down, because they would want that to be negatively charged. But if you look at all the nearby asps and glues, here's another asp, and here are 2 other asps here, those residues will want the pKa of this side chain to go up, because if you have a negative charge, you wouldn't want to have another negative charge. So what you're going to want to do for your mutation is you can compare your file with mine. So this is the wild type. So you'll want to see where your mutant residue impacts others. So, so for example, if you saw your mutation underneath these values right here, you would want to see, well, what other residue does my residue impact, and how is it different in your file than in mine? Or you could go to the residue itself. So for example, I think one of you mutated ARG110. So again, so this is ARG110, and you can see again, ARG110 is if we go back to this one, ARG110, its pKr of the side chain is, it's greater than 12, which is not surprising for arginine. But what that means is it's highly positively charged. So that means a nearby arginine is going to want this to be lower, because you'll have 2 positive charges. So again, here you can see all of the negatively charged amino acids like GLU and ASP are going to influence this by wanting the pKa to be higher, because a positive arginine will want to interact with a negatively charged aspartate. So they'll want the ARG pKr to be as high as possible. Whereas if you see other positively charged amino acids like arginine and another arginine, and I guess that's it. Oh, there's a histidine there as well. I'm going to look this up. This is listed as HID instead of HIS. So I will look this up and get back to you. I think that might mean that, so histidine has 2 conformations, delta and epsilon. So that might mean that histidine is in the delta conformation, but I need to look that up. That's just a guess on my part. So what you're going to want to do then is you're going to want to look at what contributions your amino acid makes to other residues, and then you'll want to look at your site itself and see how the pKr values of these amino acid residues are impacted. So again, if this is my arginine right here, how do these residues impact your mutation? Okay, so let me think of other things that I want to tell you about the data. Okay, one thing that I did want to show you is if I go to, okay, so this PowerPoint is on Canvas, so you can see it, is these, and this is as well. So these are some selected slides of some of the projects that the University of San Diego students did in spring 2020 when they were unable to be in lab. And one of them is you can look at these change in pKa residues, and you can graph them. So if you look at this slide right here, it's like, what can you do with H++? We're doing this right here, where we're comparing mutant and wild type proteins with respect to local environment of titratable groups. So I looked at some of the data that his students got. So because all of their mutations were virtual instead of actual, they were able to do quite a lot of virtual work. So I'm going to increase this graph right here. So this is one of the projects that one of his students did, because Now, you're not going to have as much data because we're doing real mutations, and as you know, real mutations are a lot more difficult to do than virtual ones. So if you look at this student's work right here, so this student looked at arginine 124. So now I think they were working with watermelon malate dehydrogenase, so their numbers are going to be different. But what this student did is this student created okay, like one, two, three, four, five different, six different mutants. They mutated the ARG to ALA, ARG to VAL, ARG to Phi, ARG to GLIN, ARG to LYS, and ARG to GLU. So that's what all of these different colors are right here. And then what they did is they looked in the change of the pKa values between the wild type and the mutant. And if I go back here, I think what their convention was to take mutant minus wild type. So if the mutant was higher, then the delta pKa would be positive, and if the mutant was lower, it would be negative. Um, so so what they did here was they took all of their 6 mutants, and then down here, this kind of runs together, but what they did is they looked at those selected residues, and then they looked at the change of the I'm starting to get these pop-up windows, sorry about that. So they looked at the change in the residue's pKa value with they compared the wild type with the mutant. So anyway, so if you show this in graphical form, then you can get a nice picture of of how each mutant residue is being impacted. Now you're not going to have 6 mutants, you're just going to have 1. So it looks like this student did the same thing, although yeah, so this person would have looked at arginine 130. So they would have done something that looks really similar, where they would have taken ARG 130 and mutated to all of these different residues. So so you can see that they have different clusters. So you're not going to have that much data, but you can do something similar in which you can look and see how the your mutation has impacted the pKr values of specific residues. The other thing that his students did is that they looked at various residues. So here's histidine 74, histidine 90, and histidine histidine 220, and they went back and they ran lots of H++ experiments where they changed the dielectric constant. So they went from 0 to 100. So we didn't vary ours, but you could, and you can see that some of these residues aren't impacted by the local dielectric constant, but some of them are. Or you can run other experiments where you look at the salinity. So here the student went from 0 to 1.2, and you can see these amino acid residues and how they're impacted by the salinity. So there's lots of different things that you can do. I think for us, it would be nice for our papers if everybody had a graph in their papers that looked like this, because I don't think that would be too difficult to do, is to look at your mutation and look at selected residues and compare the pKa values with the mutation and without the mutation. So I think that's all I have for now, so I hope that is helpful, and I will see you in class.